Assalamu alaikum. My name is Ammar, and today I gonna explain you about the Turing machine, its components, how it works, and its relevancy in modern computation. So let's start our video. At the beginning of the 20th century, Hilbert's challenges, specifically his Enchi-Dong's problem, decision problem, aimed to find a systematic method or algorithm that could determine whether any given mathematical statement is true or false. David Hilbert proposed a grand program to formalize all of mathematics into a finite, complete set of axioms that would be consistent, complete, and decidable, meaning that all true statements could be proven. No contradictions would arise, and there would be an effective procedure to decide the truth or falsity of any mathematical statement. But here comes a twist: this ambitious goal faced a devastating obstacle in 1931 when Kurt Gödel published his incompleteness theorems, proving that in any sufficiently powerful formal system, certain true statements cannot be proven within the system, and the system cannot prove its own consistency. Despite this, the Enchidong's problem remained unsolved. Is there a universal algorithm that can decide whether any mathematical statement is true or false? Here comes a landmark in the history of computation. In 1936, Alan Turing directly addressed this problem. He conceived a hypothetical machine, now called the Turing machine, to formalize the concept of computation and algorithms. Turing used this machine to prove that the Enchidong's problem is unsolvable by demonstrating the halting problem. There is no general procedure to decide whether a given program or Turing machine will eventually halt or run forever. This showed there is no algorithm that can solve the decision problem for all mathematical statements. Alan Turing, in the paper he published, wrote that it is possible to invent a single machine which can be used to compute any computable sequence. Turing machine is most powerful computational engine. Any computational problem which Turing machine could do, modern computer would also do, and which Turing machine did not do, modern computer did not do. This demonstrates the relevancy of Turing machine. Almost 90 years have been passed, but still in 2025, Turing machine is relevant in modern computer science. Turing machine is a theoretical construct first described and then expanded upon by their namesake, British mathematician Alan Turing. This machine can be represented through diagrams and formulas, but due to physical limitations can never be built. Various forms of Turing machines have been adapted. Now, let's discuss the components of Turing machine. The key components of Turing machine are tape, the head, state register, and transition function. Let's discuss these components one by one. The tape. The tape is an infinite length strip divided into cells, each capable of storing a symbol from a finite alphabet. The tape serves as the primary storage medium for the Turing machine and is read and written by the machine's head. The second one is head. The head is responsible for reading and writing symbols on the tape. It can move left or right along the tape, one cell at a time. The head's position determines the current state of the Turing machine. The third one is the state register. The state register in a Turing machine is like a memory box that holds the current condition or state of the machine. It tells the machine what it is doing at the moment. And the fourth one is the transition function. The transition function is a set of rules that tells the machine what to do next. Based on the current state from the state register and the symbol the machine reads on the tape, the transition function decides what symbol to write on the tape, which direction to move the tape, head left or right, and what the next state will be, what the state register should update to. Now, let's discuss the operations of Turing machine. But before we discuss the operations of Turing machine, understand that the infinite tape divided into cells and each cell only contain one symbol, which is like 0, 1 or a blank. When the Turing machine operates, it follows a set of rules called a transition function. We have discussed it in the transition function component. Here is what happens during each step. The machine reads the current state from the state register. Based on these, the transition function tells the machine what to do. Write a new symbol in the tape cell, move the head one space to the left, right, or hold, or update the state register to a new state. Now, understand this with an example. If the Turing machine is in state 0 and reads a 0 from the tape symbol, it might be told to write a 0, stay in the state 0, and move right. If it is in state 0 and reads a 1 symbol 1 from the tape, the head might write a 1, change to state 1, and move right. If it reads a blank symbol from the tape while in a state 0, it might write a 0, switch to state 1, and halt. The machine repeats these steps until it reaches a row that tells it to halt or stop. Each step is a simple update, but together these steps let the machine solve complex problems. This process models how computers work at their most basic level by reading instructions, changing memory, and moving step by step according to clear rules. Now, let's discuss why Turing machine is so important in modern computer science and why it is still relevant in 2025. The first reason is defining computability. The Turing machine clearly defined what we mean by a problem being computable. It lets us distinguish between tasks that can be solved by following steps and those that are beyond any computer's reach. This concept guides research in artificial intelligence and complexity theory. The second one is foundation of CS and algorithms. Turing machines laid the foundation for the design of programming languages and computer architecture. Their simple operation inspired the development of real computers and the idea of using algorithms to solve real-world problems. The third one is the Church-Turing thesis. This powerful thesis says that anything any computer can calculate, a Turing machine can too. It unifies all models of computation under a single framework, connecting logic, math, and engineering in a deep way. It also reassures us that today's computers are as powerful as theoretically possible. The fourth one is limits of computation. Turing machines help us find the boundaries of what machines can do. Thanks to them, we know some programs, we know some problems like the halting problem or certain puzzles in mathematics have no general solution. This teaches us to recognize when it is better to search for new approaches or approximate solutions. Now, I give you the example how Turing machine idea is used in the new generational computers. The idea of the Turing machine is so powerful that it has inspired new kinds of computers. Like quantum computers, the quantum Turing machine builds on the original concept but works with quantum bits qubits, which can exist in multiple states at once because of the rules of quantum mechanics. This adaptation means quantum computers can process much more information and solve problems far beyond the reach of normal computers, especially tasks that needs lots of calculations at the same times. Now let's talk about the practical example of Turing machine. A Turing machine is used as a model for designing compilers. For example, when a compiler reads code, it scans each character one by one, just like a Turing machine tape head. It checks each symbol, applies rule to recognize valid keywords, and translates source code into machine instructions. This idea of Turing machines is used in modern compilers as well. Now let's come to the conclusion. The enduring power of 22-year-old Alan Turing's vision. Turing machines remain one of the greatest ideas in computer science, profoundly shaping the field. They define the fundamental structure of computation and underlying logic behind every algorithm. From classical processors to emerging quantum computers, Turing's foundational principle underpin all advanced systems.
MP4 format was used in this video. Why we used MP4 format? Because clearly it has some advantages. For example, it has high visual quality and efficient compression. It is universally supported across major platforms. It is ideal for streaming, uploading and sharing. Other than MP4, there are alternative video formats, for example AVI. It have many advantages. One of them is it produces high quality video with minimal compression. It is suitable for editing and archiving. But it also have disadvantages. For example, it produces large file sizes and it is less compatible with mobile devices. Compared to MP4, it takes more time to upload, so MP4 was a better option. Now let's talk about MKV video format. It supports multiple audio tracks and subtitles. It maintains high audio and video quality, but it is not supported by all players or editing software. It produces large file size compared to MP4. Comparison to MP4 is flexible, but MP4 offers better compatibility and upload performance. So overall MP4 is our choice.